I will not talk about wavefront sensing, more about control, but in a quite basic way, I would say. But then there's MCAO, so in the end it's not so basic. So the motivation of this work is that we will have more and more tomographic systems in the future. For example, Maori, Harmony, the TMT and the GMT adaptive optic systems, just to cite the extremely large telescopes. They all, or almost all, have high sky coverage required. So we need to assess that in our simulations to design the systems. Of course, end-to-end simulations are very time-consuming. You cannot do an end-to-end simulations for every possible NGS asterism you will have. So we need mostly analytical study. So there was already something presented by Benoit earlier, so it's the same work package, I would say. So let's start from a simple case where you have the guide star that is on axis. That could be the object you want to observe. And here you see that I have the ultimate wavefront sensor, actually, because it perfectly senses the wavefront and it doesn't even interact with the light. I also have no delay, so I have a perfectly corrected wavefront. So in this case, you're happy because you have the sense turbulence that is exactly the corrected turbulence. And one way to estimate your performance in that case, that was already presented by Benoit, is to use the transfer function of your AO loop. So you have something that depends on Z that is a complex value that depends on the frequency. And so you have here a few examples with a delay of 2 for a few gain values. That is the classical integrator. And if you take that, take the square of the modulus and put an atmospheric PSD, so that is a tip, for example. Then you get residual PSDs. You do the same for the noise. There's a noise transfer function, and you get the residuals for the noise. And then you sum the integrals of these residual PSDs. You minimize it, and you obtain your optimal gain and performance. So that's the easy part. Then in a real case, of course, you will have your guide star that is not the object you want to observe. It will be off axis. So in the end, the wavefront from the object you want to observe is not completely corrected. So here you have the sense turbulence that is not the corrected turbulence, so you have an additional anisoplanatism error. So Benoit already talked about the evaluation of the anisoplanatism error. So a first assumption that you can do is that it's independent from your AO loop. And you can use the statistics of the turbulence to estimate it. You can express the covariance matrix of the mode coefficients between the on-axis direction and the off-axis direction, and you get an expression that can be analytically computed. So you can express the same anisoplanatic error using PSDs and cross PSDs, because the covariance is the integral of the PSD. So here, what I call S of for example, is actually a cube. We have for each frequency a matrix with a kind of covariance on the non-diagonal elements, and the diagonal elements correspond to the classical PSDs we are used to. So this is quite easy to derive. This is a bit less easy, but we can derive it from the expressions of the covariance. So in this case, you can express the transfer function for the residual on axis and off axis. You see that the residual on axis depends on the residual off axis. The residual off axis depends on the turbulence off axis. If you recombine, you get this weird expression that we don't really understand what happens, which we can reformulate it. And what we see is that we have the classical rejection transfer function on the turbulence on axis, and then a noise transfer function that applies not only on the noise but also on the anisoplanetic error. So the anisoplanetism is actually an additional noise for the loop. And then if you want to compute the residual, you go from this equation and you compute the residual as the trace of the covariance matrix of this residual. So it's all complex values, so we need to use a conjugate transpose. Sorry about all the equations, by the way. Someone had to do it. And you have you have this final expression when you can see the classical computation of the residual with the RTF squared and the NTF squared multiplied by the classical PSD and the noise PSD, and you have this anisoplanetism error that appears here. And so in the end, you have this expression, which is different from the previous expression. So it's just to say that the effect of the loop on the anisoplanetism should be taken into account, which is not what we're doing right now. I mean, for Harmony and Maury, but well, now we could do that. So if we look now at an MCAO system, so I'm just simplifying it to the low-order loop. So you just have a differential tip tilt on axis and on the guide stars. And you have two DMs to correct the turbulence in the volume. Here you can see that my system is not really optimal because I send the light back to the sky. But when you have several guide stars, you can have a tomography of the turbulence and correct a bit better your turbulence on axis, or in whatever direction you want to correct. So in the end, your sense turbulence is approximately the turbulence you're correcting, you want to correct. So here you have a generalized anisoplanetism error still, as known as the thermographic error. And in this case, we can compute other transfer functions. So these are matricial transfer function because we are in tomography and we need to use we need to see the effect of the reconstructor, the tomographic reconstructor, that is W here, and the projection from the DMs. So you get formulas that are not so nice to see. But in the end, we can express the residual as one RTF that filters the turbulence on axis, another RTF that filters the turbulence off axis. I didn't separate the MCAO case and the anisoplanetism error here because it's a bit complicated. But you still have an NTF that is more easier to express. Well, not that easy. And you just have the identity on the on-axis RTF, which is quite funny, I find. And these expressions, well, these expressions are not so important. It's just to say that we can have an analytical expression of the residual after the AO loop. So yeah, you can derive the covariance matrix from that. And I did a few simulations a few days ago. So with a MCAO tip-tilt loop at 500 Hertz, there's no high order correction here. I just have a least square tomographic reconstructor, 3 turbulent layers, 2 DMs. I have arbitrary wind speed and directions, and I needed to have a minimum turbulence occurrences because yeah, you need to average the effects, especially at low frequency. It gets some time to average. And you have the simulations line, the theory in dashed line. You see that the match is quite good. So we're quite happy about that. And as a conclusion, that was a fast presentation because I want you to have your coffee. And I want me as well to have my coffee. So just to say that anisoplanetism should be considered as part of the loop inputs for the residual computation. We'll discuss that in the working group, I guess. And we can have analytical expressions of this residual, and yeah, the simulations seem to confirm that. So a few perspectives. We could use another control scheme. I just use the classical integrator here. But in the MCAO, we like to use the pseudo-open loop control, especially for the higher the loop, so that we can also put inside an a priori on the turbulence. And then to implement that in the sky coverage study, so in the work package that Benoit presented as well, we can try to derive high-order corrected cross-PSDs. And then in the case of Maui, we would like to have a more accurate noise model to make the analysis completely analytical. Okay, thank you.